So just to remind you, we're not having a lecture next week, so it's a good time for you to be working on some problems and working on your final projects. So the TAs will be here, so be available 24/7.
Yeah, just walk into that big secret room and I'm probably there.
All right, let's pick up sort of where we were last. So, we've been talking last week, and we will continue this week talking about the theory of quantum trajectories, which, as we've discussed over and over, is important for both a potential numerical method for solving the master equation. So if we have the Lindblad master equation, then in principle, we can solve this equation for how the density matrix evolves by instead looking at how a set of pure states evolve, where we take a statistical mixture of those pure states. Those pure states themselves evolve stochastically, conditioned on a measurement record which we simulate based on Monte Carlo. And so, as we've discussed over and over again, this connects our idea of an open quantum system evolution to a measurement model. And so we're simulating the CP map by simulating the measurement model, okay? So there's a lot of really interesting aspects of this. We'll talk about more of them this week. One of them we talked about is, emphasizing the importance of the measurement back action that we see on a state, even when we don't see a quantum jump, right? So we talked about, the measurement outcomes are the back action that we see corresponding to the Krauss operator can be a quantum jump, but it could also be no jump. And the no jump during an interval where no jump happens, and we see that in our measurement does not register a click that would correspond to a jump, then according to the rule, the Krauss operator associated with that is the non-Hermitian type Schrodinger evolution over that time interval. And the quantum Bayes rule is you apply the Krauss operator and then you renormalize, okay? And importantly, what that means is that we have some back action in addition to whatever Hamiltonian free evolution happened in that time interval. And so, for example, as we discussed last lecture, if I thought about a two-level atom that can spontaneously emit, and at some time it's in some superposition of the grounded excited state, and after some small time interval, we're looking and we don't see a spontaneous emission, that means no jump happened in that time interval, then, well, the evolution is kind of twofold. There is the standard Schrodinger evolution, which say that there is a unitary rotation in Hilbert space depending on the free Hamiltonian. But in addition, there's a kind of nonlinear update here, which would say, according to this rule, when we did the rigmarole and we do the renormalization, that we have to take a little bit, this should be a plus. We have to take a little bit of the amplitude out of the excited state and put a little bit more in the ground state. We're hedging our bets, okay? And that update is critical, otherwise we won't get the statistics right. Because as we discussed, if at the initial time we had some superposition of grounded excited, and we measured the system over and over again, there's a chance that it was in the ground state because there was some amplitude in that state. So just because it has some amplitude in the excited state doesn't mean it will always emit. It means there's some chance it's in the excited state, but there's also some chance it was in the ground state. If it was in the ground state, then we won't see a spontaneous emission. And so this update rule is critical to getting those statistics correct, okay? And we saw another interesting application of this when we talked about the damped simple harmonic oscillator. So one of the things you're showing in your extra credit problem set is the following problem. We look at the master equation for the damped simple harmonic oscillator, which, for example, describes the way in which energy leaks out of, say, a single mode cavity, okay? And so if we prepare the system in a coherent state and we let it evolve freely according to the master equation, with this being the jump operator corresponding to annihilation of photons in the cavity, leaking out of the cavity, then interestingly, it turns out that the state is always a coherent state. It's always a pure state, and it's just that the amplitude of the coherent state evolves according to the classical trajectory. So, you know, what we would see is, you know, if we started with a coherent state, classically what happens is, you know, it will rotate around in phase space. Well, actually it rotates the other way, but whatever. You know, the minus I omega t goes that way. But the point here is that the classical trajectory goes this way, and at every point it's just a coherent state with the same fluctuations as the vacuum, and it just goes spiraling down. But it's always a pure state, okay, which is interesting because typically when you have a system coupled to the environment and it starts pure, it won't stay pure. It will become mixed, but this one doesn't. And there was an important point there. How did we understand that from the point of view of the quantum trajectories? As we said in that first equation up there, it's a statistical mixture of different trajectories evolving stochastically. And so if it's going to be a pure state, the only way that's possible is if every trajectory is actually the same, irrespective of the measurement record.
But that's because you're at zero temperature.
In this case, yes. If we were at finite temperature, then of course this would be a mixed state in general. But you know, the term zero temperature just means temperature small compared to something. That's what we always mean in physics. Nothing is ever an exact number. It's always about something being big or small. So zero temperature just means that, you know, the temperature is small compared to the temperature associated with, you know, the optical frequency. So, you know, it's always good to remind ourselves of numbers. You know, how many EV is room temperature?
1/40.
Very good, 1/40. That's something I had to learn from my oral exam when I had to learn all these things for my comps as a PhD student, and crap like that. And how many EV is an optical photon?
1.
About 1, right? So, I mean, that's tiny, a 40, you know, so we don't care about, at room temperature, there's no optical photons around that we care about in that band. Okay, so for all intents and purposes, it's zero temperature. All right, good. So, again, to remind you what we were saying last time, the way we understood this is that, you know, if we have a jump and we started with the state here, then the state post-jump is I apply this and I renormalize. But that does nothing, because this is an eigenstate of the annihilation operator with eigenvalue alpha, and that up to an overall phase So when we see a photon out of this cavity, what it says is, don't change your state assignment. According to Bayes' rule, you should keep the state exactly the same. Whereas if I have no jump, and I apply the effective Hamiltonian to it, then the state after that actually would decay a little bit, as you see. And the reason it decays is that if we don't see a photon, well, there's a chance that actually it was closer to the vacuum than I thought. I should add more to the low amplitude in the harmonic oscillator and take away some from the high amplitude of the harmonic oscillator. And again, I want to emphasize how to think about this. And in some sense, it is an operational way of thinking about what the quantum state is. For an operational point of view here is that the quantum state is just an object that tells us how we should hedge our bets. Meaning, if I'm going to make a measurement of the system, what would I bet money is going to happen? What probability would I assign to seeing a photon or not? And when I get a click, what this is telling us is, well, in the next interval, I'm equally likely to see a click. There's no change in my betting bookie assignments because of the Poisson statistics associated with the coherent state, annihilating a photon just moves the whole probability down in the same way and in no way changes the chance that I'll see a photon the next time. It in no way changes it. Whereas if I don't see a photon, then I should update things a little bit. Yeah?
So all of this is dependent on the fact that if a photon is released, you can detect it with 100% efficiency.
That's
now,
correct.
If you assume in an experimental scenario that you can't really observe the photon,
Sure.
so then what would happen?
Well, yeah, so of course, I mean, there's two aspects of this. In this case, this is a Gedanken experiment, and it's just sort of conceptual how, if we were actually trying to do this experiment and trying to then say, how should I update the state condition on what I learned, then I would have to take into account the finite detector efficiency. And which would mean that and in that case, my measurements would have multiple possibilities. Because a finite detection efficiency is like putting a beam splitter in front of the detector, which has a certain transmission to it and a certain reflection on it, right? So there's some eta which would tell me something about the detection efficiency, which would be 1 for perfect. And it's just the transmission and reflection coefficient. And so there's really a chance of seeing a photon here that I'm not seeing, right? So I can put that into the formalism, and so which would mean that my state would no longer be purity sum and have a stochastic master equation rather than a stochastic Schrödinger equation for my trajectories, because my trajectories in some sense are mixed if I'm not taking into account, or I can imagine these other channels and then average over them effectively. Okay. Okay. Very good. All right, I want to talk about another example where, this no jump probability business, just another example of something kind of nuts and crazy. Or at least not what you would have expected. You wouldn't expect that the way in these trajectories that the coherent state decays is by not seeing light. You would expect it by seeing it, right? Now, again, I want to emphasize, of course, the average energy that is lost is equal to the average number of photons that you detect, right? It has to be the case. And so there's always, you know, on average, the statistics are such that, you know, if I looked at all the trajectories, the average energy that I lose as a function of time is just, you know, the average number of photons, e to the minus, and that I would see this average number of photons in terms of clicks. But there can be a trajectory where I never see a photon. If I do that, what's the chance that if I started with a coherent state, with an amplitude alpha, and I put that, I put on the laser for a certain amount of time, the cavity rings up with a certain amount of power on it. I imagine I then say make this partially transmitting. It's perfect having to start, you know, theory land, I can do whatever I like. It's nice to live in theory land.
Or high steradian detectors.
Yeah. So now I ask, if I started with that state that had a coherent state, and I ask, what's the probability that I'm waiting, and the only way the light can get out is through the cavity. What's the probability that I'll never see a photon as I wait and wait and wait?
Zero, right?
No, actually, interestingly, it's not zero.
Probability density squares.
So the probability that I never see a photon,
So use Bayes' rule or something.
I
When you
could
say
do that.
when you say never see a photon, is it at t tending to infinity or?
10 t tends to infinity.
Oh,
I start with the coherent state. What's the probability that I never see a photon?
Was actually in the ground state.
Exactly, which is the vacuum. So this is equal to the probability that it's in the vacuum, which is what? E to the minus alpha squared. Okay, and that's not zero. Now, of course, if alpha was reasonably big, that's so small it could be minuscule. But if I, you know, put on just a tiny bit of intensity, then, you know, I have a good fraction in the vacuum, some amount with 1 photon, some amount with 2 photons, with the probability of seeing n photons, you know, is going to be given by the Poisson distribution. Right? And that has finite probability when n equals 0. So just because I have intensity doesn't mean I have any photons. That's an average quantity, but there's fluctuations, and in principle, there's no photons in there at all. And there's a chance that could happen. And I have to see that with that fraction, otherwise it was the wrong statistics. Interesting. All right. So let's talk about another example. An example we talked about last semester, and we're going to revisit. And that, before I do that, I forgot, man, I got a lot to do. Crap, better stop talking, move. All right, here we go. All right, so we talked about the idea of Monte Carlo wave function simulation, right? And, you know, we wrote that in terms of we have some state at some time t, and we update this to the state at time t plus dt, either according to no jump or jump, where the no jump probability, you know, we apply as we just said, we apply this guy to it. And this we apply this to it, and then we renormalize. And we have to decide, if we have a jump, we have to decide which of these jump happen by doing Monte Carlo. Okay, so first we can ask jump or no jump, and if a jump happens, then we can decide which jump happened by dividing the interval from 0 to 1 into different intervals of size depending on the probability of that jump, and then throwing the computer dart at it and seeing where it lands and deciding which jump operator to. Now, this is tedious because, you know, at each little time interval, you're asking, and you want this time interval to kind of be pretty short so that you can capture something that approaches a differential. And each time you ask the system, did you jump? And it's going to say, what do you mean? You only gave me this tiny amount of delta t. The chance of me jumping is tiny. Why? And then you ask it, did you jump? You just asked me. It was like nothing. Why? You just keep asking, and you're wasting all these precious random numbers. And there's no reason, because we know the chance of it jumping in that tiny interval is pretty small. So it'd be much better if we can have a more efficient way of asking, what's the chance? We would better to have something called the waiting time distribution, which would say the following. Given a jump happened at time t, what is the probability of the next jump happening at time between t plus tau and t plus tau plus delta tau, okay? So we can't ever say a jump at a specific time because that's a set of measure 0. We need to think about it in a finite interval. So the point here is here's time t, and then we're asking, we want to say there's no jumps until this next little interval at time t plus tau to t plus tau d tau, okay? And we say the next jump happens in that interval, and there's no jumps before then. So that we will call, that waiting time density, we'll call that probability W t plus tau given t d tau, okay? So this is a probability, this function is a probability density. It's the probability per unit d tau that the next jump will happen at time tau later, given that it happened at time t. If we can sample from this probability distribution, this is what we call the waiting time distribution, that I have to wait a time tau for the next jump, and I'm promised that there won't be any jumps until a time tau later in the next little interval. If I could sample taus, then I can just have continuous time evolution according to the effective Hamiltonian for this interval, and then when I roll the dice and I see where that time is, apply the jump operator then. and then apply the appropriate Hamiltonian of H effective over the next time interval until I expect the next jump. So it's a way of simulating the jump times, okay? Instead of asking at every interval, I just say, I know there's not gonna be a jump until this next interval. So the goal is, how do we determine that? Well, we can ask something, there's something else that's easy, and from this we get this, which is, I ask you the following question. Given state psi at some time t, what is the probability that no jump happened from t to t plus tau? Yes, you have a thought about it?
There is a probability of some jump happening, so you can subtract it from.
You could, but it's kind of the other way, you're right, but there's a more direct path here, because this is over a finite interval. So, let me ask you a slightly different question. What's the probability that no jump happened in the time interval between t and t plus dt?
You do the continuous evolution and find the overlap.
Right, so we know that that is, by definition, by Born's rule, this is equal to the probability of no jump in this little time interval is the expected value of the POVM element, which is K dagger K, or M dagger M, I'm sorry, I'm calling it M, not K. Which is the norm of M0 delta T acting on the state squared, which is e to the minus I H effective delta T. So the norm squared of the decaying wave function is the probability that I don't see a jump in that little time interval. Right? That's what we were just been talking about. So now I repeat the question. What is the probability that no jump happened in this finite time interval? Well, that means that in every little delta t, there wasn't, so it's just the product of all of those. And that would say the probability of no jump from t to t plus tau is this. Is this. Right? And that's so if I had the state at some time t, the probability of not jumping from t to t plus tau is the norm of the wave function after that time interval with this non-Hermitian evolution. Okay? And this, of course, is equal to 1 minus the probability that there was a jump. Right?
No, right? Because you can also have 2 jumps or 3
Well, I
jumps.
didn't say there wasn't at least one jump, at least some
Okay,
jump.
okay.
There was some jump.
Uh-huh.
There was some jump. right? Could be more than one, absolutely. However, this is, I can think about this as the cumulative probability right? So that's, there could be more than one jump, but if I look at the integral of this probability density between time t and time t plus tau, that's the probability that there was at least some jump, a non-zero jump between that, okay? Now, given this, I can simulate how I sample from this. And that is something that took me years to understand, and I don't know why it took me years to understand. A decade, I don't know why I was confused about this, but it's because it was just given to me, no one ever, I don't know, I never had a course in statistics, and, sorry. So, let me just do a little aside on something. Suppose I have X. So there's a method sampling from a probability density using the cumulative distribution. Okay, so let's suppose P of X is a probability density on the interval X between 0 and infinity. Okay, it's a real number. That's positive. Okay? Or non-negative, doesn't really matter. And I want to sample from this. One way I can do that, you know, is, because of course it's a probability density, it's a mass function as it's sometimes called. I mean, have to think about that. But a kind of direct way is possible is based on this so-called inverse method, based on the cumulative. So let me define f of y is the probability that x is less than y, or equal to, okay? It's also greater than 0, but let's just say that. So it's in a finite interval. It's somewhere between 0 and y. That's, of course, the integral of that. So if I can sample from this, I can sample from this. Okay, and the way I do it is the following. So let's look at the cumulative probability distribution. So it, you know, it goes to 1 as y goes to infinity. So here's some y, here's f of y. All right? So I want to sample from the x's that are weighted by this probability density such that I get the right, this is of course the derivative of this, right? So what I can do is I take R is a random number between 0 and 1. Okay? Here it is. There is the inverse of that, which is, I'll call X. It's the image of R. Okay? Now, the probability that R is less than f of r, I'm sorry, f of y, is what? If r is a random number, uniformly distributed between 0 and 1, what's the probability that this is going to be less than this?
Just F Y.
It's just what this is, right? It's f of y. F of y is the fraction of 1, right? So the probability that this is going to land between that is the value of f of y. But that is equal to this. So the probability that x is going to be less than y is this image, okay? So the probability that so if I can find what this x is, I'm going to be sampling from the right probability distribution. So x is sampled from the probability density. So by using, if I can do this inverse, then I can sample from the probability density through this method. And we can do that thus because we have the cumulative probability. We have 1 minus it, but then it's kind of the reverse. So now I'm going to write g of y is 1 minus f of y is the probability that x is greater than y. Okay? And that's the same thing as, so if I look at some y here, and here's g of y, then when I throw a random number r, the probability that r is less than g of y is equal to g of y, which is equal to this probability, which gives me a way of sampling it. God, it took me forever to figure this out. This was in Zoller's original paper on the quantum jump method, and he just did this. I'm like, what the heck? Anyway, I don't know why. All right, so what that means for us is the following. For the Monte Carlo wave function method, instead of in every little time interval, dt, asking jump, no jump, what I can do is instead simulate the waiting time. So an alternative method for quantum Monte Carlo wave function is to simulate the waiting time to the next jump. And the way we would do that is the following. So say at time t, the state is this. And I want to say, when am I going to see the next jump? What do you suggest, given what we just described? Well, what I'm going to do is simulate this, because I have this. So what I have is 1 minus the probability of some jump between t and t. This is the probability of no jump. Which we said was this. It's the decaying norm That's the probability of no jump in that interval. Which is what we just said over there is 1 minus this. Okay. And we want to sample from this, but we can sample from this, from this. This is like g of tau, what I wrote up there. So the way I would do it is pick a random number r that is uniformly distributed between 0 and 1, and then evolve in time until this is less than or equal to r. So what you want to do is, on this picture, you start at, it's at 1, and then the normal decay, and when it hits r, you say jump. So instead of asking jump, no jump, you'll evolve the system forward in time, check its norm, see whether the norm is less than this. If not, keep evolving, check if the norm is less than this, keep evolving until your norm dips below this. Then what do?
Jump.
You jump. Thank you. Because at that time, I jump. So until t, then apply the appropriate jump operator. Then renormalize, and then rinse and repeat. Okay? Now, of course, did I really save anything by doing this? Because I have to make my delta t sufficiently fine that I don't kind of miss this time, right? Because if I evolve too quickly in time, then I can go past r and miss the time of the jump. So I've got to kind of, you have to think about the numerics of that, of how I can refine, get fine enough. I mean, I always want to evolve for a fine enough delta t so that I capture the appropriate dynamics. But how small delta t must be to both, see what I want to see in the time dynamics, but also get the statistics right, is a little refined and different in these two methods. And also means I don't have to, at every time, calculate, the same jump probabilities. You'll play around with it in your numerics, and you'll see how it goes, and see what,
I imagine you could do some sort of binary search thing, like evolve
Exactly.
over time, go backwards, forwards, and
You could do stuff like that. And you can also, depending on how determinist, you can calculate this whole thing once. If it's the same initial state every time, then you just calculate that one curve one time, and then just see when you cross it. Now, it's not the case when you have multiple jumps that your initial state is the same after the jump, but for the two-level atom, it is, because when you jump, you're in the ground state. So sometimes it's easier. Yeah.
So all the physics is in the effective Hamiltonian. That describes your system.
That's right. I mean, your effective Hamiltonian describes, there's two pieces of the physics. The Hamiltonian and the jump operators.
Okay.
Okay? The effective Hamiltonian is a combination of the Hamiltonian and the jump operators. So the physics is in both things. Very good.
Not really, right? Because when you calculate that norm, the Hamiltonian part is cancelled out. So the only part is
No, it's, I mean, in terms of, what the norm is preserved in the Hamiltonian, but the combination of the Hamiltonian, I mean, when we evolve, this norm will depend not just on the imaginary part, but the real part as well. This thing is evolving, in a way, like if I have a Rabi oscillation, the chance that I jump or not jump, will depend on how often I am in the excited state, which I'm changing by driving. Because the imaginary part is this, but the chance of being there is caused by, say, a driving term. So the norm decay depends on both the real and imaginary parts. All right, let's continue. And I want to talk about another example where crazy stuff happens. I was going to use a different word that started with S, but I started with stuff. All right. So,
Crazy science.
yeah, that's exactly what I was thinking. That's the other word.
Science is the fail.
All right. So, let's remind ourselves of something we talked about last semester, the idea of coherent population traffic. Okay, so let me remind you what we discussed. You remember that when we have something like a lambda level structure. So I have an excited state, and then I'm going to have two ground states. We'll call them GA and GB. And let's say that there is some field I can apply that couples this ground state to this level, and there's some Rabi frequency associated with that. And I have another field that connects these two levels. It could be because they're different frequencies, different polarization, will come to that, but at the moment, just make it just abstract. And this guy can decay either of these levels with some branching ratio. So there's a rate gamma A and there's a rate gamma B, and they add up to the total lifetime. Gives me a total rate of spontaneous decay out of the excited state, which is the sum of those. Okay? So the Hamiltonian for this system is, well, I have some coupling that couples me between the ground states and the excited states with the appropriate Rabi frequencies. And if I rewrite this, we can rewrite this as a coupling, which I'll write in terms of some omega tilde, between a state I'll call the bright state and the excited state, where the bright state is equal to omega A GA plus omega B GB divided by omega tilde, where omega tilde is the normalization. Okay. So this state Rabi oscillates between the excited state and some superposition in this way. I don't have to start in that superposition, but if I did, I would have that. There's another state, so this is the bright state. There is another state, which is your father, known as the dark state. Sorry, I always make that joke every single time. And that the dark state is given by the orthogonal state to the bright state. So the dark state is orthogonal to the bright state, and this two-dimensional Hilbert space spanned by these two states could also be thought of as some superposition of the bright state and the dark state. The dark state is dark, why? Why is it called the dark state? Because it's uncoupled. If I started in this particular superposition, excuse my horrible handwriting, it's just gotten worse and worse. If I started in this particular superposition and I turned on the lasers, it would be dark. It wouldn't couple to the excited state, it would just stay there, okay? Now, we studied this in homework last semester, one of your favorite assignments. Every assignment is your favorite assignment. And we looked at the master equation for this, where we have two jump operators. There's a jump operator associated with spontaneous emission on this transition, which jumps me from an excited state into A, and there is a jump operator associated with spontaneous emission on B, right? Those are the two possible jumps we could have. And H effective is H minus the sum of the jump operators as we have discussed, and this is this, where gamma is the sum of those, right? So we'll decay out of the excited state. We decay out of the excited state with the total rate gamma, which is the sum of the rates gamma A and gamma B. And I might jump here, or I might jump there. And then whether I jump here or whether I jump there depends on the branching ratio, which we would calculate with the Born rule, right? So we would calculate what's the probability to jump, and then we'd say, well, given there was a jump, I might have gone here or I might have gone there. There's a fraction of times it goes there to there, which is related to the ratio of gamma A to gamma, okay? And what we found is that when we solved the master equation, that in steady state, the system ends up eventually in the dark state. So if we solve the master equation, which we did last semester, we didn't use quantum trajectories and the like, but we just said, here's the master equation, let's just solve it. And we found that in steady state, as t goes to infinity, the state goes to the dark state. And we called that coherent population tracking, or CPT, because you can think about it as through this absorption and emission process, eventually the population is trapped. It will no longer absorb and emit, and it's trapped in a state that is a superposition of these two levels, and it's a coherent superposition. It's not a statistical mixture of either being in A or in B, but it's a particular superposition with a particular phase that is critical for that state, now unable to absorb a photon again. And so it's sort of like there's a hole in, you know, the world, and if once it falls in, it's out of the picture. And so that's what was called, it was discovered in some spectroscopy experiments in France, and was called by the French CPT. All right, so let's think about this from the point of view of quantum trajectories, okay? So let's say, we'll come back to this. Let's just say, for simplicity, that omega A equals omega B, okay? Doesn't really matter, but let's just, let's think about that. So that the bright state is equal to the symmetric superposition, and the dark state is the antisymmetric superposition. Okay. And let's say that at t equals 0, I start, say, in the ground state GA. Okay, so I'm going to drive the system here at the system. And now I want to ask, we know that in steady state, the system is going to end up in the dark state, because that's the solution we found to the master equation. And if in steady state that is the case, then every trajectory must, in the long time limit, be in that state, right? So how do we see this in terms of the quantum trajectory based on these jump operators? Okay, so at time t, I want to know, in a given trajectory, what's the probability of being in the dark state? I start in this state. This state is a superposition of the bright and the dark state. It's, in fact, a 50-50 superposition with this particular phase as I've chosen it, right? Okay, so at time t equals 0, it's here. The probability of being in the dark state is a half. Then what happens? Well, I'm driving the system. And so what can happen? So during the time I'm not seeing a jump. Well, that means that as the system evolves in time, I'm evolving, I'm putting some excited in the excited state, I'm putting some in here, it's going back and forth. But at the same time, I'm taking population out of the part that can excite, that can decay, and putting some population into stuff that can't decay. And so what will happen is, during the no jump evolution, I'll start evolving towards the dark state, because there'll be more population that is put in here. This stuff, the dark, I'll start amplifying the amplitude here. This guy will start coupling to the excited state, but that fraction will change, and some more will be dark. Now suppose a jump happens. what happens? Well, there's a chance it might jump here, and it's a chance that it might jump here. If I jump here, I'm back to where I started. If I jump into the B state, well, that state, according to this, is also a 50-50 superposition, but with just the opposite phase, right? This minus that. So regardless of which jump happens, after the jump, I go back to this state. And I start again. Maybe, oops, I saw a jump, and now, oops, I saw a jump, and then eventually I will get to 1. But I get to the dark state by not seeing a spontaneous emission. Yet again, it's the no jump evolution that does that. Yeah.
Okay, you said you're driving the system. What drives the system?
I'm putting a laser on.
Oh, you're
So
pumping
that's
it.
what these arrows
Oh,
are.
you're pumping it.
I'm
Okay,
pumping it.
sorry.
Yeah, I'm sorry. I'm putting it when I say a drive in. So our Rabi frequency couple omega corresponds to, you know, the dipole matrix element dotted into the electric field of the laser.
Okay, got it.
So I'm driving with the laser, and that's what one does in this coherent population trapping. It doesn't matter what the initial state is. The steady state is independent of the initial state. We could start in any initial state, and eventually, in steady state, I'll be in the particular superposition corresponding to whatever the weight, you know, this particular weighting, okay? But in this example, in the quantum trajectory formulation, based on this particular set of jump operators, the way in which we would get into the dark state, given this initial condition, is by not seeing the photon. Interesting. Now I want to spend a few minutes to end this lecture of a specific example of that, which we're going to then look at in the next lecture. All right. Yes.
I'm just a little, so like, why does the dark state correspond? Is it because like you're basically, the dark state is like the ground state that we know we started in, probably? Or
It's the ground state that doesn't couple to the light.
Okay, thank you.
So because it doesn't couple to the light, the more we don't see a photon, the more we have to hedge our bets that, you know, it's because, you know, we have some chance after every one of these jumps, there's actually some chance that it was in that superposition. After each jump, either I'm here or here, and after each jump, there's a half chance that it's in the dark state. Because either this or that is actually a superposition of this and this. And there's always a chance that actually it's in the right superposition, and the longer we don't see a photon, the more we hedge our bets and say, yeah, amplify this amplitude, de-amplify that one.
So, like, if I were constructing this dark state, how do I know that that's what a state that doesn't come to light? So have you already?
The way we know that is that the Hamiltonian, another way of looking at it is that the dark state is a state which has 0 eigenvalue. It's annihilated by the Hamiltonian. So if you look at this, the antisymmetric superposition has no coupling to the excited state.
Okay.
Yeah.
Thank you.
Yeah. Alex?
I have a practical question.
Yeah.
In these types of experiments, is it hard to distinguish, the emitted photons that you're looking for from the light that you're using to drive the system?
Well, I mean, generally the answer is yes, if, the question is, what fraction of photons are emitted into the solid angle that defines the laser? It's going to be very hard to block out those laser photons, but it's a tiny fraction of 4 pi seradians if I have a pretty collimated beam.
Well, I would think you would still get some of the driving light like scattered off the atom that would be hard to distinguish from.
Well, scattering off the atoms is spontaneous emission.
It is? Okay.
That's what spontaneous emission is. It's absorbing and emitting. Any light, if it scatters off something else, like, Tim didn't align the beam splitter right and it scattered off the edge, that's bad news. But scattering off the atoms is spontaneous emission. It's
Okay.
absorbing that photon and re-emitting that photon. Yeah.
Can't you also distinguish it through polarization, because any spontaneous emission photons will be unpolarized, and your laser
That's not
driving
quite true. We're going to talk about that actually now. So, what we'd have to talk about, let's talk about a very specific example to think about what photons, what are the different qualities of photons we might be talking about. These need not be, at the same energy even in this most generic case, okay? But let's talk about a very concrete example in the last 8+ minutes, okay? So let's consider an example of an atom with a multiplet of magnetic sublevels. And we're going to do a little atomic physics right now, okay? So let's imagine we have a state where the ground state has a total angular momentum, I'll call J. Now, don't think about this, it's the this could be hyperfine. I just say it's a total angular momentum. And so the ground state has a J equals 1. And so that means that the M of the ground state can be -1, 0, or +1, okay? So this is my ground multiplet. And I'm going to have an excited multiplet which also has a total angular momentum of 1, okay? All right? And so now my different transitions, say if I have a lambda transition like this, correspond, as Tim was suggesting, to different polarizations of the laser, okay? So, for example, let's say that I have a laser beam, here's this K vector, and it's linearly polarized. And I choose to define the quantization axis of the atom to be the direction of propagation, okay? Then the light is perpendicularly polarized to the quantization axis. I'm choosing this. I'm not putting a magnetic field on. I'm just calling them. These are just labels. So I'll call these are the Z projections, right? So it has +1, 0, or -1 angular momentum along the direction of the K vector, which I'm calling Z. When I drive this with linear polarization, and I'm in either one of these states, I can only drive light that is driving perpendicular to that, which is to say it is either sigma plus or sigma minus. So that means this is a superposition of sigma plus and sigma minus light, okay? There is no component of the light which is along the quantization axis. okay? So if I started in 0, I would drive this, okay? So those are the only things that the laser drives. It can take me from 0 to +1 through a sigma plus. It can take me from 0 to -1 through a sigma minus. It could take me from -1 to 0 to a sigma plus, or from +1, right? And then I can spontaneously emit in different directions. So if I start here, I can spontaneously emit like that. That's a pi photon, which means that the photon is oscillating with like this, okay? And it already has some component along that direction. Or it can emit like that. It can never emit from here to here because the selection rules tell me that I cannot change m by more than 1. If I start here, I can in principle go here and here and here. And if I start here, I can in principle go here or here. Okay? Yes?
When you say you can't change m by more than 1, is that like to first order, like if only looking at dipole matrix elements?
That's correct.
So, okay, that could be like a quadrupole transition?
Yeah, I mean, so to degree, this is a hugely dominant effect, and we would see no, since this can't happen in this case because the quadrupole moment for this transition is 0. Because J, I can't have, because they would have, if this is a dipole allowed, electric dipole allowed transition, this one has to have an L and an L prime. This has to say like be an S state or a P state, and there's no dipole matrix element. So along this transition, there is none at all. It's only dipole allowed, electric dipole allowed. This is electric quadrupole forbidden. So I couldn't change M by 2 at all in this case.
Is that kind of like just something that is common when you pump, or like can you pump to quadrupole
You can.
kinds of states?
You can.
And how often would you like be looking at that situation? Like how useful is it to know?
No, that's something one typically would want to do if one wants to be in a level that has a very long lifetime. Okay, so it depends. If I'm, wanting strong transitions and I want dipole, if I want weak transitions, I might want electric quadrupole or magnetic dipole transitions. But we digress. All right, so I guess I'm running out of time, but I just want to say the following thing. So, one of the things, the question of what the transitions are and their relative strength is determined by the addition of angular momentum. Because I'm starting with a state that has certain angular momentum, I go to another state that has some angular momentum, and I've added or subtracted angular momentum from the photon. So we consider, if I look at the dipole operator, I can look at that dipole operator projected between the excited state and the ground state. So this is where this is, the sum over all the states with the different magnetic sublevels, and similar for the ground state. Okay. So what's important here is asking, what is the matrix element of the dipole, electric dipole operator between these different states? And to do that, this is a vector operator. It has different components. And what this matrix element is depends on the component. And the way one does that is from the Wigner-Eckhart theorem. Who doesn't love the Wigner-Eckhart theorem? It's my favorite. And the Wigner-Eckhart theorem tells me I should decompose this operator not into Cartesian components, but into the so-called spherical basis, where E0 is EZ, and E plus or minus 1 is minus or plus EX plus or minus I ey over root 2. So this is what we call pi polarization, and this is what we call sigma plus and minus polarization relative to the z-axis. This is a basis in three-dimensional space that represents a vector along z and two complex vectors in the transverse plane. And when I do that, I get that this matrix element is the component of a vector with component q relative to this basis. It's also known as a rank 1 tensor with this component. And so now I ask you, what is this matrix element according to the Wigner-Eckhart theorem?
That's a
It's going to tell us all
Klebsch-Gordon
about it
coefficient,
in our
It is a-
fancy exam.
It's a Klebsch-Gordon coefficient?
That's right. So what this is a Klebsch-Gordon coefficient that says I start with an angular momentum J with projection M along the quantization axis. I add to it a photon, which has an angular momentum magnitude of 1 and projection Q along the quantization axis. And I end up with a total angular momentum J sub E. And what's left over is what's called the reduced dipole matrix element. And I always like to use this convention for the Wigner-Eckhart theorem, also known as wet. And this is what's known as the reduced. Now, this is a whole bunch of atomic physics and quantum mechanics that one day maybe I'll teach again. But for now, we just sort of say this is what it is. This is the Klebsch-Gordon coefficient. As seen in Mathematica. And it tells me about the addition of angular momentum. It says, I start with a certain angular momentum of the atom, I add to it the angular momentum of the photon, and I find out what's the amplitude of having this much angular momentum afterwards in the atom, okay? And of course, this Klebsch-Gordon coefficient is non-zero only if JE is equal to JG or one more or one less, and ME has to equal MG plus Q. And that's where the dipole selection rules come from. It's from the Klebsch-Gordon coefficients. If this was a quadrupole, then there would be different angle. It would be a rank 2 tensor, and it could do more things. Okay? So what that tells me is that the different transitions for whether I go along, from this M state to that M state is weighted by the Klebsch-Gordon coefficient associated with that transition. Now it turns out that the Klebsch-Gordon coefficient for this transition is 0. And that's actually a general rule. If I have the same angular momentum, the 0 to 0 transition is forbidden. It's one of the ways we do optical pumping at the clock stage, but that's another story. And so what that means is that if I start in this or this state, I can forget about this and think about this as a lambda transition of the kind we just discussed. And we'll pick that up next time to see how to go back to Tim's question about polarization and all of that. And importantly, the thing we haven't yet talked about, but boy, it's an important point, I can't believe we haven't got to yet, is the story about different unravelings of the master equation. It's a really still part of the story, and we'll do that on Thursday. Yeah?
So the photon only has angular momentum if it's perfectly polarized.
It only has a non-zero projection of angular momentum. It always has one unit a photon has h bar of angular momentum, right? But that's the magnitude is 1 h bar. But the projectile angular momentum can be +1, -1, or 0. So if I have something which is, say I have this propagating like this, then it has 0 projection of angular momentum along that direction. But it has ±1 along that direction.
Okay.
Yeah. All right, I gotta get to the seminar.